name is Jack Porter. I'm the engine development and support team lead here at Epic Games Korea. And my topic today is optimizing the Unreal Engine for Sol demo for mobile platforms. And the Sol demo, which you probably haven't seen, although there are a few YouTube videos of it, is a small demo we put together for GDC this year to kind of push the boundaries of what was possible on high-end mobile phone devices. So, I'll begin. So first of all, a little about me. I'm originally from Australia, but I moved to Korea in 2003, so I've been here for more than 10 years. And I was one of the founding members of Epic Games Korea. But my Unreal Engine history goes a very long way back. I started working at Epic Games headquarters while we were making Unreal Tournament with Unreal Engine 1. And I've worked on all versions of Unreal Engine for about 15 years. So today I'll show you a video of the Sol demo. I'll talk about the devices we were targeting and then how we made the demo and the optimizations we made using next-gen mobile rendering techniques. So Unreal Engine 4 is known for this quality of graphics. This is a screenshot from the Infiltrated demo. And the challenge is how to bring that to mobile devices. And I'm not going to talk in that much detail about the mobile rendering pipeline because Sang-Woo Lee just did that in the previous session. But instead I'll talk about, from the Sol demo, the kind of problems we had getting that kind of content to run, high-end content to run on the latest mobile phone devices. Okay, so what is Sol? The purpose of Sol was to show what's possible in mobile rendering on high-end mobile phone devices, on both iOS and on Android, on ImageTech, Adreno, and Mali GPUs. And we wanted to push the limits of draw calls and driver features to try and get the mobile industry to innovate and improve their drivers. And we intended this to be used as a benchmark, so we expect this demo to come out as an OpenGLES benchmark sometime in the future. The next most important thing about it is that we tried to make it using a regular PC content pipeline. And what I mean by that is instead of building the entire environment in 3D Studio Max, maybe by one person per level or that kind of construction method that you would use for a smaller scale game, we wanted to make sure that we could use a regular PC kind of content pipeline with reusable assets in a similar way you make a PC MMORPG. So I'll show you a demo of the Sol, video of the Sol demo before I talk about it some more. If we have some time at the end, I'll show it running on my iPhone device, but I think it's probably quicker to show the video here now. We got the sound? For some reason, sound doesn't do it. Anyway, it's just background music. But the point is, we wanted to get very high quality environments with all of the reflections and those realistic high dynamic range lighting that you've seen in Unreal Engine, and wanted to push those features on the latest mobile phone devices. So we also wanted to support large outdoor landscapes that you would need to make an MMO type game or a game RPG. And we needed to run it all at 30 frames per second. So the target devices we were targeting were the iPhone 5S, and the Nexus 5. And although they're both quite competing phones, especially in the Western market, the specs are quite different. They've got different GPUs, got very large difference in the amount of pixels they have on the screen, and there's even twice the amount of RAM in the Nexus 5. The Nexus 5 is pretty much the same spec you'd find in an LG G2, for example. It's almost exactly the same phone. So the process was, we wanted to choose the target frame rate, which we said would be 30 frames per second, and we wanted to run in native resolution on the iPhone 5. If you look over here on the right, comparing the iPhone 5 resolution, which is this many pixels, up to the full HD from the Nexus 5, it's so many more pixels, and actually the GPU work scales to the number of pixels. So we felt there was no way we could target full HD. So instead we targeted 720p, which is about 26% more pixels. It's a little bit bigger than the native iPhone 5S resolution, but it's quite similar. And then after we'd chosen what devices we're going to run on, I did a whole lot of performance testing. And this was in the very early days of Unreal Engine 4 mobile development. So I actually used Unreal Engine 3 just to get some idea about the number of draw calls and the number of triangles that were possible at the time. And I did things like rendering thousands and thousands of different textured cubes in some space to see what the rendering cost was. And I came up with about 500 draw calls and about 400,000 triangles currently possible using OpenGL on those two devices. And then we went on to plan and develop the content, and we wanted to focus features that were not possible until now, such as image-based lighting and outdoor environments. And then finally, after we developed the contents, we needed to fix bugs and optimize it. So, to give you some stats, the APK size for this is about 500 megabytes with 500,000 draw calls per frame and 300 to 400,000 triangles every frame on a play area of about 2 kilometers by 2 kilometers. And we're using the Unreal Engine level streaming system to hide and show different parts of the environment when they're not visible. And using that kind of system, we think this could be scaled up to make a much larger game like an RPG. So if you look in wireframe, it's a bit dark, but that amount of geometry is actually a very dense number of triangles. So this is a screenshot of the editor running the Sol level, and I just wanted to point out that a couple of things. Firstly, here an individual object is selected, so it's being built out of individual reusable parts the same way you build a PC online game. And using this kind of construction methodology is important for high-end games on mobile as they become more and more complicated, because it's no longer possible for one person to do all of the artwork. You need a team of people, and they all need to be working on assets at the same time. They need to contribute to the same content. So in the same way you have large numbers of people making MMO games, you need a large number of, if you have more than a few team members, you can still make some very high-end quality games and allow them to work in such a way that they can work together. So, as was mentioned in the previous session, forward rendering is used on mobile instead of deferred shading. And we think that the bandwidth cost is just too expensive for multiple render targets, even using OpenGLS 3.0. So that kind of limits the number of dynamic lights that you can have. So we think high-quality static lighting is still the way to go. So we use global illumination captured on PC. use the image-based lighting. We use the cube maps also captured on PC with this physically based shading model that was described in the previous session. So I think you saw this before, except mine doesn't have cute animals down the bottom. This is some output from Unreal Engine's physically based shading model that we also use on mobile. At the top line you can see is transitioning from a very kind of plasticky object to a metal object, and the same with roughness. From no roughness is a mirror all the way to some brushed aluminium for a metal, and for a non-metal it's a shiny billiard ball all the way to some rubber at this end. So we wanted to retain this shading model on mobile as well as PC, but we had to make some adjustments. So there's some more approximations in it compared to the PC version, but it still looks very good on mobile. So the material pipeline, the artist creates the material shader in the Unreal Editor tool using these nodes here. There's a big difference between Unreal Engine 3 and Unreal Engine 4. In Unreal Engine 3, we didn't used to support the user being able to create custom material graphs and make a customized material that way. Instead, you could just select different kinds of effects you wanted, specular on a specular, and normal map on a bump offset or a bump offset. So instead of that, the full Unreal Engine material is generated, and on PC, that graph generates some HLSL code automatically. And it's not very pretty to read, but it's parsed by the HLSL compiler. This particular function is get material base color, and it's called by the HLSL code that we've written for the physically based shading model whenever it needs to get the base color from the material. And on PC, we can execute this code directly because PC uses HLSL. But on a mobile device, we have to use GLSL. So we actually cross-compile the HLSL to GLSL. And one of the things you'll notice, this is defining here some input textures and input parameters, and it specifies the precision here as being high precision. That's one of the things we had to do was automatically generate the correct precision that we need. So in general, we try to use low precision because it's a lot faster. If we were to use high precision on all of our materials, there's no way we would run at 30 frames per second. Also, there are different versions of GLSL. This is a version 3.0 pixel shader, or fragment shader as they say in OpenGL. The fragment shader for OpenGL ES 1.0, which is, the fragment shader version 1.0 is used in ES version 2. That has some quite different layout. So we generate that and adjust that code using a preprocessor. So we can support both ES2 and ES3 devices. But there are some problems with this. Because the shaders are compiled by the device, every individual device has a different shader compiler. So there could be bugs in that shader compiler on people's phones right now, and you wouldn't know unless you tested on those individual devices. Sometimes we can work around the bugs, or we need to change the shader. One particular thing we've seen on some devices is that register allocation can be very slow. So you might have a material that works great on an iPhone and on an LG G2, but when you run it on a Galaxy S4, it's a completely different GPU, different shader compiler. The shader compiling suddenly takes a very long time. We've actually seen some shaders take 5 or 6 minutes, whereas before they're instantly compiled. Also, some extensions that we might need might not be available. The texture LOD extension is used to choose the roughness for our image-based lighting. And the frame buffer fetch extension we also use And that's used when we want to blend some translucent object like a particle, and we want to blend that nicely with the environment. To do that without frame buffer fetch is very slow and mobile, but frame buffer fetch lets you go and read a pixel directly from the frame buffer immediately. So we use these extensions when they're available, but if they're not available, then maybe the result won't look as good. So for Sol, we felt that we really wanted to make use of the image-based lighting feature of Unreal Engine 4. And it's not just in the reflections on the floor, but all of the reflections on the environment on this wet pillars. So that's why we decided to make a kind of a wet underground area to start in so that you could see those image-based lighting features. So, as you may have heard, the image-based lighting is captured on PC and stored in a cube map. On PC, we can use 16-bit cube maps or 16-bit floating point textures for the cube maps. On mobile, we don't want to do that. We just use 8 bits per channel, and we have a special encoding that we use to store a better high dynamic range version of the cube map. And as Samuel Lee mentioned in the previous session, the mip-map that you choose is based on the material roughness. So, you probably know that mip-maps, you have a high-resolution version of a texture, and then you have smaller versions of that same texture. And they're typically used to reduce texture bandwidth, but we're using them for a different purpose here. We make the high-resolution version of the texture really sharp and a very perfect mirror reflection of the environment. And we make the lower bitmaps more and more blurry versions of the environment, up until the lowest bitmap is a very, very blurry version of the environment. And that lets us select the particular bitmap we want to render with to choose the roughness. Now this selection needs to be done every time you are shading a pixel in the fragment shader. So we have to use a GLSL instruction telling it to which bitmap that we want to sample from the cube map. So where we can, we use OpenGLES 3.0. That's available on Arduino devices, high-end Arduino devices and high-end Mali devices, like the T628, which is inside the Galaxy Note 10.1 2004 edition. And when ES 3.0 is not available, the alternative we have is this extension called GL Texture, Shader Texture LOD, which is supported on the iPhone 5S. So here you can see the perfect reflection on the left, and on the right, as the image gets more and more rough, it gives much more blurry result, which gives that roughness feeling. So, to optimize the image-based lighting, the first consideration was cube maps. And so, the cube maps use a lot of memory because there are 6 textures for each cube map, and we need a lot of them. And in fact, in Sol we have more than 44 megabytes of them at the moment. And so we settled on 128 by 128 as a good trade-off between quality and size. We also, on PC, because we have so much more GPU power available, we do some really fancy work to blend between 2 different cube maps, or a number of different cube maps. So, if you've got a room, you could have a cube map sample here, and one here, and one here, and as the player walks down the room, you want to switch between this cube map to this cube map to this cube map to this cube map, but you want to do it in a way that it blends smoothly. So, on PC we can do some parallax correction using texture arrays to solve this problem. But unfortunately on mobile, we didn't have that ability doesn't exist because there are no texture arrays. So we decided that we would have to have a single infinite distance cube map per object rather than having the set of cube maps that are blended between. We also have an option to completely disable the specular lighting from the CubeMap for fully rough materials. So especially the outdoor terrain kind of materials, they don't need any specular reflections because they're simulating dirt or grass, and disabling that specular CubeMap saves us a lot of GPU time. Apart from just the number of triangles and the amount of GPU time, memory usage was also the biggest concern for the Sol project. The main problem, as you probably know, on mobile devices, there's no virtual memory, so if you ask for memory and it's not available, your app will crash. And it's actually difficult to get an idea of how much memory is available to your app. Even on a 1 gigabyte device, there's a lot of memory being used for it's being used for frame buffers of the operating system and other things running in the background apps. So sometimes we were getting memory warnings after just 400 megabytes of memory that we'd allocate. If you look at the total amount of rendering resource usage in this demo, you see it's almost 400 megabytes. So the vertex and the index data is basically the triangle information. They've got the render targets, which we use for the intermediate rendering steps. But we have a lot of 2D textures, 264 mega of them. We do have the cube maps as well. So our solution was to look at those 264 megabytes of 2D textures and perform texture streaming. So if you look at the breakdown here, a lot of them are diffuse textures. We've got some normals, lots of shadow maps and light maps, and just a little bit of terrain blending maps. And of course we use the standard texture compression formats that are available on each device, but unfortunately the solution, this doesn't give us enough of a saving, so the only solution we have is to stream textures from disk or from flash memory. So for Sol, we set up a 100 megabyte texture pool, and we're continually streaming textures in from the background. So out of those 264 megabytes of textures we need for the entire demo, we can save 164 meg of RAM just by limiting that pool to 100 meg. Unfortunately, there's no standard way to implement this on OpenGLS ES. And it might seem easy to load some data from the flash memory, but the actual problem is you want to have an existing texture at low resolution, and you want to load bigger bitmaps and keep the existing bitmaps. Similarly, when you want to stream out a texture, you want to save the memory from the bigger version, but you want to keep all of the smaller versions of the textures. So on iOS, we can do it because they have an extension that we actually asked for a long time ago. Apple implemented this extension which allows us to copy texture data from one texture to another. So we make a smaller texture and we copy the bit levels across. And I've been working with ARM, the people who make the Mali GPU, and they also have support for texture streaming using this GL texture base level and text image 2D, setting a null texture to load and unload individual textures or individual bitmaps into a single texture. But unfortunately, there's no support in Arduino at the moment. So things like the Nexus G2 or the Galaxy Note 3, those kind of devices are not currently able to support this kind of texture streaming. On PC, we use 32-bit frame buffer. It's probably mentioned about this mosaic exposure in the previous session. So we'd like to use a 16-bit frame buffer on mobile for floating point, but sometimes that's not available. For example, the Mali T628. So we have this mosaic exposure technique that, for neighboring pixels, so this pixel will be rendered using a 0 to 2 dynamic range. This pixel, bright pixel, we rendered, so it's capturing the bright objects in the scene, whereas the neighboring pixel will only capture the dark objects in the scene because it's being rendered with a 0 to 1/6 dynamic range. And then, using this method, we're actually capturing the very bright and the very dark parts of the scene, and we can make quite a good blended version of that using the demosaic pass to simulate linear blending. It also saves memory using that the lower bits per pixel frame buffer. So for directional lighting, we use directional light maps, and we have a special encoding for those. I won't go into details about that because I don't have that much time, and I want to talk some more in detail about the terrain rendering. So this is an overhead view of all of the terrain that's in that particular level from a particular viewpoint. And you can see when you look in wireframe, the wireframe has a lot of detail in this kind of area, and that's the play area where the player gets dropped off. And this is the region around the player, and this is the region that's far in the distance. And we have an automatic LOD system that smoothly morphs between each of those LODs. You can actually see some LOD morphing going on in the background. So, because we need to support that continuous LOD, we need to support the height data for each LOD. And we do that by storing the extra data in the vertex data that we interpolate in the vertex shader. So I actually use 14 bytes per vertex. And for lighting and blending, we do both of those with the texture. So the tangent basis and the blend maps are being done using textures, and that way there's no discontinuity when you're changing LOD levels. So no matter what LOD level, the lighting and the texture is always going to look exactly the same. The artists have also done some clever texture packing. Here are their base colors, but they also pack their normal maps into a single texture by only using 2 of the channels. We also have procedural blending, which saves texture memory for a blend map. This allows us to give extra detail. So in this case, we examine, here's some snow, and we look at the angle of the surface, and the tops of the surface we continue to allow to receive snow, but anything on an angle, we decide that it should not have snow. So this is an example of the procedural blending. And this is the procedural blending added to the weight-based blending that the artist have actually painted. Now, landscape, as I said, which is our train system, it uses a continuous LOD system. And to avoid duplicating data, I want to store the vertices in such a way that I can reuse their data for the multiple LODs. So here's an example of a transition. This here is a single chunk of landscape, and this is LOD 3, which has 16 vertices. And as it's morphing, the vertices are slowly being morphed to the target's locations until the end where you just have the remaining vertices. But if you look at the vertex numbers, vertex 1 and 2 have disappeared, and just we have 0 and 3 remaining. So this caused a problem on the ARM Mali chipset because the driver looks at all the vertices that you want to transform, and it looks at where they are in the vertex buffer, and it transforms all of the vertices in the middle. So it's a bit of a simplified example, but here I've got this vertex data, and the white versions is the high resolution, and the orange version is the low resolution, and these are the vertex numbers, right? So this is the vertex buffer that we're going to share, and the ones that in bold are the ones that are used at the low resolution. So it's just this vertex, this vertex, this vertex, and this vertex. Okay, so for LOD 3 we use all of the vertices, but for LOD 4 we only use vertices number 0, 3, 12, and 15. These are the corner vertices, right? So, as I as I said, that causes a problem because all of these vertices are going to be transformed regardless of whether or not they're being used for a particular LOD. So the solution was just to rearrange the vertices so that the ones used in the ones shared between multiple LODs are placed first. So this is just a rearrangement. So 0, 1, 2, 3, the corner vertices are numbered first, right? And then when you render a low resolution version of the height map, you end up using just this section of the vertex buffer, and the vertex shader can run much more efficiently. So this rearrangement increased our frame rate on this particular Galaxy Note 10.1 device from 10 frames per second to 30 frames per second. There are also different, some more challenges that we have trying to get our software to run on multiple devices. And that is the differences between the shader compilers and the workarounds, as I mentioned before, but there are also different performance characteristics. So on some devices it's very expensive to allocate resources. On other devices it's not so expensive. Some of them have higher draw call overheads. This is a continuing problem. Another problem we have is thermal throttling. So if you run your game, the game uses a lot of CPU and GPU power and makes the device hot, and then the device has got a little temperature sensor in there, and it automatically reduces the clock rate. And that thermal throttling allows the battery to last longer and keeps the device cooler, but it makes your game slower. So we need to avoid these kind of situations. Finally, version fragmentation. Many Unreal Engine 4 versions are solved simply by doing a firmware upgrade on Android. So updates are the biggest software, the biggest problem that we have on Android. The fact that updates are very slow to come out, especially for older devices. So in the future, iOS 8 is going to have the Metal API, which you saw drastically reduces the CPU overhead. It doesn't change the GPU overhead, though. And we demonstrated that earlier today, as well as at the Worldwide Developer Conference. And the other option is running, it's not quite the full OpenGL stack, but it's basically the full OpenGL renderer, including deferred rendering if it's possible. We demonstrated that on K1. So in the future, even higher end device and even higher end features are going to be possible on mobile devices. So the time to think about the high end is now, because people are buying new phones faster than it takes us to develop games, so we really need to be considering the next generation. Okay, I think I'll, if I can, I'll just switch the cable and launch the Sol demo on the device. I didn't prepare my phone, so it's going to upload some apps that were in the background first, which is why loading takes a bit longer than it should. Okay, so this is running real time at 30 frames per second on my device. I won't look at the big screen, it's very hard to control. So as you can see, we've got the full dynamic environments using those reflection captures. And as I walk through the environment, I'll jump to some different parts, just to give you an idea of what's possible. This is a high dynamic range statue we've got here with a very nice reflection capture. You might have seen there in the background there was a little bit of texture streaming. That's because I jumped to that location, so when you walk through it, the texture streaming is not so obvious because it can happen instantly. Is our kind of outdoor vista. Unfortunately, the other problem I have here is this HDMI cable actually slows down the demo. So unfortunately, it runs a lot smoother with the device disconnected. If you'd like to come and have a look when I step out, if you want, when I finish, if you want to come and step up the front, I'm happy to show you what it looks like on the device. Somewhat more impressive than on the screen. Okay, so I'll take some questions if anybody has any, but I think we're quite short of time.
이제는 이제 경계가 점점 이제 프로그래밍을 하면 뭐 안 되겠다. 아티스트 쪽.
Okay, I guess there are no questions. So thank you very much.
두개 다 했어. 두개 다 하고. 저는 뭐 때문에 프로그래밍 들었더니 결국은 두개 다 해요. 프로그래밍 그냥 뭐 익히 알던 거니까 그냥 그러려니 하는데. 아티스트 쪽은 분명히 들어봤던 건데 와 저게 왜 여기서 나오냐고 이런